everyone, welcome to the lecture on radioactivity. So radioactivity is a very important topic, especially for the exams like IIT JAM, or you talk about the GATE examination. And for both these examination, radioactivity plays a very crucial role. So in this lecture, we will attempt to understand each and every aspect which you need to know for the radioactivity. So let me begin. So radioactivity, first of all, we have to understand what is radioactivity. So we have to understand the meaning of radioactivity. So our first purpose is to understand the meaning. Okay. So what do I mean by radioactivity? So basically, you have seen in movies, you have heard the news, you have seen that there is something known as nuclear energy. There are something known as nuclear bombs. There is something known as radioactivity. You can call as radioactivity poisoning, or you can call it as the uh, radioactive hazards. All of these things you might have heard. So what happens is, usually when we have a big nucleuses, so we have big nucleuses, for example uranium, for example thorium, all these are the natural sources of radioactivity. So radioactivity is defined as the spontaneous decay of nucleus. So what do we mean by the word spontaneous? So spontaneous means something which happens by itself. Something which will happen by itself is known as spontaneous. For example, the water of the river falling down. So this is a spontaneous process. You do not need to supply the energy to do this process. So the spontaneous decay of the nucleus will be basically, we mean as the radioactive, sorry, we call it as a spontaneous, which whatever is happening by themselves or itself. Okay. So now there are multiple sort of radioactivity we have familiar with. So sometimes what happens is that you have a nucleus. For example, let's say uranium. So you have a uranium nucleus. Now what will happen is it will decay. What do we mean by decay? Decay means it will, so let's say the mass number of uranium is 232 and the atomic number is 92. So it will basically decay. Decay basically means it will convert to some other nucleus which is much stable than that, and it will emit some other particles, for example alpha particle, beta particle, and so on. So basically from inside the nucleus, some amount of neutrons and protons are coming out. As a result, the nucleus itself is changing into some other nucleus. That is basically the meaning of decay. And this decay is happening automatically, or you can call it as spontaneously, without providing any extra energy. Okay. So there are basically three kind of radioactivities we will study. One will be alpha decay, other will be beta decay, and last one will be gamma decay. Okay, and in to understand these three decays, we need to know the basic principles of radioactivity. Okay, so let me first make a chart which describes that what kind of nuclear decay modes we all know. So let me make that chart. So nuclear decay modes. So nuclear decay modes. So first of all is alpha decay. Then in the list comes beta decay. And then in the list comes gamma decay. These are the three decays which occur in the radioactivity. Okay. And in this, beta decay is also characterized in three more subcategories. One of them is beta negative decay. One of them is beta positive decay, and another is electron capture. We will study about all these three very nicely. Also, the gamma decay is also characterized in three possible ways. Number one is gamma decay as such. Another is known as internal conversion. We call it as internal conversion. We will study what is internal conversion. And third of it is basically known as internal pair conversion. Internal pair conversion. Okay. So these are the three basically subcategories of gamma decay, and we will study about all these three. Okay. So now, before we jump into the understanding the alpha beta gamma decay, we have to first understand the basic principles of radioactivity. So there is one of the most basic or fundamental principle which is basically known as law of disintegration. Law of disintegration. What is the law of disintegration and what does it tells us? So there are two basic assumptions of this law. One of the assumption is, now there is a, you let's say you take a sample. So you have a sample. Let's say this is a sample of uranium. And now you have a sample of uranium and inside there are many uranium nucleuses, right? And every nucleus wants to decay, or you can say every nucleus wants to disintegrate. There is some tendency due to which these nucleuses wants to disintegrate themselves, or these nucleus wants to decay themselves. Now, first law says that there is an equal probability, there is an equal probability for all nuclei, for all nuclei of sample to decay. Okay, so let's say there are 10,000 nuclei in one sample, then there is an equal probability for all 10,000 nuclei to decay. Whatever is the probability of decay of the first nuclei, same is the probability of decay of the second nuclei. So the probability of decay of all the nuclei is exactly same. This is first law of disintegration. Then the second law, which is much more important and which is basically more or less mathematical, it says that rate of disintegration is proportional, rate of disintegration is proportional to the nuclei present, to the nuclei present in the sample. Okay, and this is very interesting. This is very interesting thing. So let's say you have a radioactive sample. Okay, what is rate of disintegration first of all? So the rate of disintegration, let me underline this and let me open up it here. Rate of disintegration basically means that number of nuclei disintegrating, number of nuclei disintegrating per second. How many number of nuclei are disintegrating every second? So let's say 10 nuclei are disintegrating every second. Then the rate of disintegration will be 10 per second. This is also known as the activity. This thing is also known as the activity. So let's say you have a sample, and in this sample your nuclei are disintegrating. So rate of disintegration is written as dn by dt, which basically means how many nuclei are disintegrating per unit time. So dn by dt. Now this thing will be proportional to how many number of nuclei you have. Let's say your sample has 100 nuclei. Okay, and let understand this analogy what I'm trying to give you, and this is a very important thing. Let's say you have 100 nuclei. Okay, so you had a rate of disintegration as 10. It means every second 10 nuclei was decreasing. So after 1 second, what will happen? So let's say, let me draw this thing here. So let me show it here. So at t equals to 0, there were 100 nuclei. But the rate of disintegration was 10. It means every second 10 nuclei are disintegrating. So after 1 second, what will happen? You will be left with this 90. So you are only left with this 90 nuclei. Will the rate of disintegration remain same? Is it still 10? The answer is no. Once your number of nuclei inside the sample reduces, then how fast the nucleuses are decaying will also be decreased. So now there will not 10 nuclei will not disintegrate every second. Only 9 will disintegrate every second. So after 2 seconds, what will happen? You are left with this 81. Now the activity is not 9. Now not 9 nuclei will not disintegrate every second. Now only 8 nuclei will disintegrate every second. So after 3 seconds, how much you are left with this? You are left with this 73. Now again, the how many nuclei are disintegrating every second will reduce even more, and this pattern will keep on going. So clearly you can see that how many nuclei will decay every second, or you can say the speed of disintegration of the sample depends upon how many nuclei are there in the sample. Okay, so it is like a brooming, right? So let's say you sweep your entire room and you are collected a lot of dust. Okay, now you want to collect that dust and throw it away. So what you do is you collect your dust. In first time, a lot of dust comes out. Then you throw it away. Then in the second time, less dust is coming up. Then you again throw it away. In the third time, even lesser dust comes out. Then you again throw it away. So now in each time, how much dust you are collecting will keep on reducing. That is the same thing happens in a radioactivity. So the law which basically suggests is that our dN by dt, which is means the rate of disintegration, depends directly on the number of nuclei present. How many number of nuclei are present at this moment? We will put negative sign, and there is a very basic reason for that. Why we put negative sign? The reason being because our nuclei are reducing. So Dn is negative, right? So our number of nuclei are reducing. That is why we put a negative sign. Okay. So our basically law suggests law of disintegration suggests that dn by dt is equals to minus lambda n. This is your law of disintegration, and you have to remember this law. What is lambda here? Lambda is the proportionality constant. So when I removed the proportionality constant, I come up with the constant which is basically lambda, and lambda is known as the decay constant. Decay constant. Okay. So this is basically decay constant, and its units are per second or per minute, whatever it is, per unit time. These are the units of decay constant. Now, I hope that everyone will remember this. So, I already told you that dN by dt is known as activity, which is basically A. So, another formula to remember here is that activity is equals to minus lambda n. Okay. Now, we will use this law to answer a very, very specific question. And what is that question we want to answer? And that question is, let's say at time t equals to 0, we had n naught nuclei. So when the time begins, we have n naught nuclei. So to begin with, we have n naught nuclei of any radioactive material, of any radioactive material. Let's call it as any radioactive material. Let's say uranium. Okay. How many nuclei will be there? So the question is, how many nuclei will be there after time t? So once the time t has passed, so now the time t has passed, after some time your number of nuclei will keep on reducing, reducing, reducing. So after time t, how many number of nuclei will be left? That is the question which I want to answer using the law of radioactive disintegration. So I will use the equation which is being known, which is very famous equation, and which I told you that you have to remember, which is basically dN by dt equals to minus lambda n. So this is a fundamental law of radioactive disintegration. Now what I will do is I will separate the variables. So if I separate the variable, I bring variable n on one side and I bring variable time on other side. I get something like this. In the next step, I do an integration. So I can do an integration. Initially, I had n naught number of nuclei, and finally I have n nuclei. I start from time t equals to 0, and now I come up to the time t. So these are my integration limits. Now you know that integration of dn by n is nothing but ln n. and this is your limits, which is basically n to n naught, and on the other side you get minus lambda t. Okay, so if you put the limits, you get ln n minus ln n naught equals to minus lambda t, which is basically you can write it as ln n by n naught equals to minus lambda t. Now, if you take exponential on both sides, you will get n by n naught equals to e raised to power minus lambda t, or you will get n equals to n naught e raised to power minus lambda t. This is one of the very important crucial law. It basically tells you that after time t, these are the number of nuclei which will be left. So after time t, how many nuclei you have? You have n number of nuclei. At time t equals to 0, how many nuclei you had? You had n naught number of nuclei. It basically, from this equation, this is one of the another equation that you have to remember. From there, I can say number of nuclei, I can say number of nuclei in radioactive sample, number of nuclei in radioactive sample decreases exponentially, decreases exponentially. So you can clearly see that number of nuclei in your radioactive sample is decreasing continuously, and it is decreasing exponentially. So if I draw the graph, okay, let me use a proper graph. So if I draw the graph, okay, so if I do this, on the x-axis I plot n, and on the on the x-axis I plot time, and on the y-axis I plot n. Then at time t equals to 0, you had n naught number of nuclei. As the time passes by, your nuclei keep on decreasing, 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 exponentially decreasing, and ultimately it becomes 0 at infinity. So your nuclei, number of nuclei in the sample are decreasing exponentially. They are decreasing exponentially. This is one of the very important relation we need to know. Okay, so this you have to keep in mind, that this relation. Okay, now we define our parameter, which is very important. I call this as activity. We have to talk more about activity. Okay, and activity, basically I told you, is nothing but dn by dt. How many nuclei are disintegrating every second? That will be basically activity. So if that is our activity, then what we will do is, n we already know what is n. N is equals to n naught e raised to power minus lambda t. Okay, our activity is not dn by dt. Our activity is ideally defined as minus dn by dt. Activity is defined as minus dn by dt. This is the definition of our activity, and n naught we already know. If I do dn by dt, what will I get? If I do dn by dt, I will get minus lambda n naught e raised to power minus lambda t. If you differentiate this thing, you will get it. Then what about activity? It will be negative of this, so it will be lambda n naught e raised to power minus lambda t. Okay, and this thing will be basically, this is n, right? This is n. So our activity will be nothing but lambda n. This is one relation. Another relation is this one, or you can call this relation as a equals to a naught into e raised to power minus lambda t, where a naught is lambda into n naught. So these are the relations that you have to keep in mind, that activity equals to lambda n naught e raised to minus lambda t, and lambda n naught can be written as a naught. So your activity after some time t, right? So this is your activity at time t equals to 0. The nuclei are decaying very fast. Nuclei are decaying very fast. But after some time t, your activity reduces. Activity reduces. So this is your activity at time t. And your activity is decreasing exponentially. You can clearly see that your activity is decreasing exponentially. So this is the things we learned. Okay. So this is how do we visualize from the graph, from this graph, that our activity is decreasing exponentially. So let me show you that thing, that how can we visualize this. So from this equation, you can clearly see that activity is nothing but the slope of n versus t graph, right? Because differentiation gives you slope. So activity is nothing but the slope of n versus t graph. Okay, and you can clearly see in the beginning the slope of the graph is very large. You can clearly see, and as you keep on moving forward, your slope keeps on going. All your slope keeps on decreasing, and ultimately at infinity your slope becomes zero. So the slope of the graph is decreasing. It means the reactivity of your sample is also decreasing, and that is something which we need to take care of. Okay, so we basically have to understand that in our sample, how many nuclei we have will keep on reducing exponentially. Also, the speed at which they are decaying is also decreasing exponentially. So these are the two important relations we derived. Okay, now we will extend this logic and we will cover our next thing, which is basically what are the units of activity. And this is very important because sometimes the examiner has tried to give some other units so that student makes the mistake. So the SI unit is basically becquerel. Becquerel was the person who discovered the radioactivity. So becquerel is a unit, SI unit, and it is defined as 1 BQ. So 1 BQ is nothing but 1 disintegration per second. 1 disintegration per second, which basically means per second. So how many disintegrations per second? 1 disintegration per second is known as becquerel. This is the most fundamental unit, or you can call it as the SI unit. Okay. Now, usually what happens is in day-to-day our life, the radioactivity are usually in gigabecquerel. Gigabecquerel means 10 to power 9 becquerel. Megabecquerel. So the radioactivities are usually in this range. Mega means 10 to power 6, right? Usually we do not see that radioactivity is in 1 becquerel, 2 becquerel. That something is not visible as such. Okay. There is another unit which is basically the traditional unit, and that is Curie. So Curie is another unit for activity, and it is defined as Ci. The unit of Curie is Ci, and it is defined as 1 Curie equals to 37 gigabecquerel. This is the conversion. Okay, because when Curie discovered the radioactivity, the range in which she observed the radioactivity was basically in the gigabecquerel. That is why the 1 Curie is equals to 37 gigabecquerel. Giga means 10 to power 9. Okay. Similarly, there is another unit which is basically Rutherford. So all these units are basically defined after the names of uh, our scientists. So one Rutherford, how much is one Rutherford? So one Rutherford is basically 1 megabecquerel. Okay. So if you do the 10 to power 6 becquerel, that will give you 1 megabecquerel. Okay. So that was about the basic ideas of, you can call it as, um, about the activity. Now let me bring one question so that we can do one question here, and that will give us a very good practice of the things. Okay. So let's do one problem here. Okay. So this is a problem I want to cover. So let me zoom this image so that you can look at this problem. So this is our problem. So the problem says that half-life of the radioactive isotope. Okay, so we have to cover half-life first. Okay, let's complete that. Then we will come to this problem. Okay, because it is too soon to come to this. Okay, let me come to this again. Okay, so we will come to this afterwards. Let's first complete our idea. Okay, now next thing which we want to study is half-life. Okay, we want to cover what is half-life. Okay, let's do it. Half-life. Now this is one of the very important parameter for the, you can call it as from the radioactive point of view. What is half-life? Amount of time amount of time after which our sample becomes our sample becomes half of initial value. Half of initial value. So let's say you begin with 100 nuclei. So initially you had 100 nuclei. How much time afterwards you will have 50 nuclei? So after how much time all you will be left with only 50 nuclei, because number of nuclei continuously decreasing. So after some particular amount of time you will be left with only half of the initial value. So that is basically defined as a half-life. Okay. Since it is life, the unit of this will be seconds. Okay. So now let's see what we can add in, how we can find the formula for half-life. Now we will come with our same formula which we have studied, n equals to n naught e raised to power minus lambda t. Okay, n equals to n naught e raised to power minus lambda t. So at time t equals to half-life, so when the half-life is gone, number of nuclei left with will be half of the initial value. So after half-life, how many nuclei are left? Only half of the initial value, which is basically n naught by 2. So I will put my value of n here, which is basically n naught by 2 equals to n naught e raised per minus lambda, and my time is equals to t half. Okay, so if I cancel n naught on both sides, on this side I will get 2 minus 1, and on this side I am getting e raised per minus lambda t half. Now I can take log on both sides. If I take log on both sides, I will get, so first of all I can bring this negative, so I can bring this here and I can bring that here. So basically I will get e raised by lambda t half equals to 2. Okay, so I cross multiplied, nothing else. And then what will happen is I take the log on both sides. So if I take the log on both sides, I get lambda t half, and on this side I get ln 2. Okay, so from there I basically get that t half is equals to ln 2 by lambda. This is one of the most important formula for half-life. Lambda we already know is the decay constant. Okay, and the value of lambda 2 basically, which you should be familiar with, this 0.693 divided by lambda. So sometimes you have to use this as well. Okay, so what does it tells us? It tells us that if delta decay constant is more, nucleus will decay fast. Nucleus will decay fast, or you should say that sample will decay fast. Your sample will decay fast. Why? Because if the lambda is more, then t half is small. T half is small, because you can clearly see there is an inverse dependence on this. So if the lambda is more, t half is small. T half is small means in less amount of time, your sample will become half. Right? If in the small amount of time your sample is becoming half, it means your sample is decaying very fast. So if lambda is more, decay is fast. Right, because the half-life is small. Half-life is small means this sample will become half of it in very quick time. Right, however, if the lambda is small, it will decay slow. The sample will decay slow. Why the sample will decay slow? Because now the t half will be more, which basically means it will need more time to become half. Sample needs more time to become half. It means its decay is slow. So that is something we need to know about the half-life. Okay. Now there is another kind of life which we define, and that is basically known as the average life. I'm not giving you the proof of this, but average life is also important. What is average life? On average, what is the life of one nucleus? So let's say you start with 100 nucleus. After some time you are left with this 90, after some time you are left with this 70, after some time you are left with this 30. So your nucleus are keep on reducing. So some nuclei decayed immediately, like the moment you started it decayed. Some nuclei decayed after some time. Some nuclei decayed even after some more time. It means every nuclei is living for different lives. The lifetime of each of the nucleus is different. Some nucleus are decaying immediately, some nuclei are decaying after some time. Decaying of the nucleus means the death of the nucleus. So basically the life of each of the nucleus is different. Then there will be some average of life. Means what is an average life of nucleus? It is just like humans. Some humans die at the early age, some humans die at the larger age or the older age. Then what we say that what is an average lifespan of a person? Similarly, what is an average life of a nucleus in any particular sample? And that is basically defined as tau equals to 1 by lambda. You can do the mathematics to prove this out, but if you will do it, you will be coming out as 1 by lambda. Okay. So the half life, sorry, average life is defined as 1 by lambda. Okay. So this was about the basics of the radioactive nuclei. Now we can come up here and we can basically solve some of the problems so that this gives us the good practice. Okay. So let's solve first question. So the first question says that half-life of the radioactive isotope is 4 into 10 to power 8 years. So half-life is given to us, which is basically 4 into 10 to power 8 years. Okay. And if there are 10 to power 3 radioactive nuclei, so they are saying today. So if there are 10 to power 3 radioactive nuclei in the sample today we have 10 to power 3 radioactive nuclei. The number of radioactive samples 4 into 10 to power 9 years ago, initially how many nuclei were there? So if it is given that number of nuclei today are equals to 10 to power 3, and we need to find that what was the initial number of nuclei. So we need to find n naught. N is given to us and half-life is also given to us. And basically time is also given. So in time is given as 4 into 10 to power 9. Now we can use our very traditional equation, which is basically n equals to n naught e raised to power minus lambda t. If we use this equation, we come up with n is given to us, which is basically 10 to power 3. N naught we do not know, exponential minus lambda t. So let's find lambda t on the side. So what will be our lambda t? So lambda t is defined as ln2 by half-life into time period. Okay, so this will be our lambda t. So ln2 is ln2, let's write it ln2. T half is given to you, which is 4 into 10 to power 8. Right, and time period is given as 4 to 10 power 9. If I cancel 4 I am left with this 10 ln2, because 10 to power 8 will cancel 10 to power 9 and I am left with this 10. You know this property that a log b is equals to log of b raised to power a. So I will do is I will bring this 10 inside and I will raise the power to the 2. So basically I will get lambda t equals to ln 2 power 10. Okay. So my lambda t comes out to be ln t to 2 to power 10. So with that said, let's put the value here. Lambda will be ln 2 to power 10. What about negative? So negative will also go and become the power. So if the negative also goes and become the power, you will get e raised to power ln 2 minus 10. Sorry. Okay. The feature does not work very well. Okay. Anyway, it becomes 2 to power minus 10. Okay. So now what will happen? Exponential and log cancel each other out. So you are left with this 2 power minus 10, and on this side we have 10 to power 3. So if I bring 2 to power on other side, I will get 2 to power 10 into 10 to power 3. Now what is 2 to power 10? It is, I think, 1080 into 10 to power 3 nuclei. So your answer is 1080 into 10 to power 3. Sorry, 1024. 2 to power 10 means 1024. So your answer is 1024 into 10 to power 3. Okay. So initially you had 1024 into 10 to power 3 number of nuclei. Okay. Now let's solve another problem. So let me bring this problem here. So let me bring the problem here. So let me zoom this it so that you can read the question. I hope it is clear, visible to everyone. Yeah. So the activity of the radioactive sample is decreased to 75% of its initial value after 30 days. Okay. So in 30 days, the activity reduced to 75%. Let's say initially it was 10, so now it is only 2.5. Decreased to, oh sorry, decreased to 75%. Not decreased by 75 but decreased to 75, which basically means if initially the radioactivity was 100, now the radioactivity activity is 75. So the activity at time t is 75% of initial value. Whenever you have to resolve percentages, you have to divide by 100. So if I divide 75 divide by 100, I will get 0.75 a naught. So my activity is equals to 0.75 a naught, and the time is given to me, which is basically 30 days. And now they are asking what they are asking. They are asking that what is the half life of the sample. So I will use that formula, a equals to a naught exponential minus lambda t. This is the formula I will use. So if I use this formula, I will get a equals to 0.75 a naught, initially a naught exponential of minus lambda t. I will put the value of time in the end. So if I cancel a naught and a naught on both sides, I will get this is 3 by 4 and this is basically exponential minus lambda t. Okay. So now what I can do is I can bring exponential lambda t on this side and I can bring 4 by 3 on the other side so that negative cancels. Now I will take log on both sides, so I will get lambda t into ln 4 by 3, which is basically log 4 minus log 3. Okay. And this is basically equals to lambda is equals to log 4 minus log 3 divided by t, right? And log 4 and log 3 is given to us. Log 4 is 1.4 and log 3 is 1.1. So this is basically 1.4 and this is 1.1 and time period is 30 days. So basically this comes out to be 0.3 divided by 30 per day. Per day, because time period is given in days. So this will basically becomes 1 by 100 per day, right? And now I will say that my t half, which is my half life, is given by ln2 by lambda, right? And ln2 is 0.693. 1 by lambda will be 100 multiplied by day. So my half life comes out to be 69.3 days. This is my half life. So let's check the answer. So my half life comes out to be 69. Okay. So this was another question. Okay. So these were some of the problems based on the radioactivity. Okay. In the next class, we will discuss the successive radioactivity. Means sometimes what happens is, let's say uranium disintegrate into thorium, then thorium disintegrate into polonium. So radioactivity is happening in steps. First, one nuclei decay into second nuclei, then second nuclei decay into third nuclei. So this thing becomes the successive radioactive disintegration. In the next class, we will study that, and in that, I will give you the important formulas. Okay. So with this said, I say goodbye for this class, and I will see you in the next lecture. Bye bye, everyone.